Okay. Work top to bottom, or you want to jump to something? For those of you who have kind of looked this over, is there something you want to jump to, or you just want to go top to bottom? Top to bottom? Okay. So all the relationships. Okay. We have all of our relationships. What is the equilibrium constant for the below reactions? Go ahead and write it. Go ahead and write it. Yep.
I think I got this, but this one's just a better problem to go. You know, it's got a lot in it. The volumetric analysis one.
Mm-hmm.
You've got time for that one today.
Okay.
Because it's a waste.
Could also, you could also work on it, and then if you don't get it right, we'll do it on Friday between 12 and 1. And you get more out of it if you struggle on it, Zach. You'll remember it better. Instead of just watch, like, seeing me write down the solution, I think if you struggle on it's better. Okay, so K is products over reactants. I guess the only trick here is what? The P's, because they're gases. So I guess you'd lose a point if you didn't use P's, because that's what the book wanted, right?
And does CO2 count as its element?
Well, the only thing you leave out are what? Solids and liquids. Oh, and H2, hydrogen squared. And H2 isn't a liquid. Well, sorry, it's supposed to be P. H2O is a gas, so it's in there. You got to square it. Right? Products over reactants. From the equilibrium constants K1 and K2, calculate the equilibrium constant for this reaction. All right. There's got to be a game plan for this. What was it? Eric says multiply K1 and multiply K1 times K2. Does that work? Yeah, there's two ways that you can look at this. One way is you just, add them up and you see that the oxalates cancel. But that's really not the healthy way, because it seems like, well, what do you do with the K's? Right? The healthier way might be to actually, let's write this. Well, if you can remember that section in class, I don't know how many weeks ago, if you add equations, you end up multiplying the equilibrium constants. But if you don't remember that, you might actually just have to write the equilibrium constant for this one, write what K1 is, write what K2 is, and then if you multiply them together, you'll see that those factors of hydrogen oxalate cancel. So it's just K1 times K2. And then you'll end up with the K for what's up above. Okay, it actually does work. Just to prove it to you. Right? If you multiply these together, right, the intermediate cancels out, and you end up with squared the oxalate all over and that is the same as the K for this guy, right? So it is, it's just multiplying the K's. You see how that works? So it actually works. That's why we multiply them. So your answer is whatever K1, what'd you get? K1 times K2 is 2.916 times 10 to the negative 6. sir. Right? You comfortable with that?
That's basically the same thing.
Yeah, it's just mathematically it makes more sense for me to do this than to, otherwise there's memorizing, right? If you add them up and this cancels, it doesn't tell you to multiply these two. But if you do it, if you take a look at it this way, it makes more sense to me. Okay, this guy's principle, the chandelier. Okay. Put your answers next to these. Will more or less, what is that? C3H6? Will more or less C3H6 react? Okay. Under each of those conditions. You're at equilibrium, and then they mess it up. They added some nitrogen gas. Will more or less C3H6 react? Maybe you don't want C3H6 to react. So. Circle your answer on each of these. Oh, I forgot. We have our, well, I don't know if we may not have time to take a quiz anyway, because I have that quiz from last time, but we may not get around to it. All right, let's wait and see. The first one less. Okay, so you add nitrogen, it's going to shift it over here. So we're going to have more of this C3H6. So essentially less will react, because it's the react thing, right? Maybe let's just forget this less. Well, that's what we're stuck with, right? Well, more or less react. You're going to have more of this C3H6, right? So then less of it's going to react. It's pushing it this way, right? Less of that C3H6 would react. Does that make sense? You're pushing it which way?
So wouldn't that mean that?
Remember that the equilibria are dynamic. So let's think of it the pushing way. Does everybody agree I'm going to end up pushing it this way? Does everybody agree? Right? So that means C3H6 is going to have a lot harder time to go that way. So I'm pushing it that way, so it will be less will react.
So you have more reactant, and less of it's going to react.
Yeah.
I think that's the part that confuses will it more or less react. Usually it says
Okay, so
Yeah, I know. Usually it's in terms of product. I know.
Or no,
So
usually it's just in terms of amount.
yeah, but this is just as equally valid, right? You could be very interested in a reactant. That C3H6 might be extremely expensive, and you're interested in them. So you add a lot of nitrogen. It shifts the equilibrium over here. So that means that C3H6 it's not going to go forward and react hardly at all. The reaction is shifted this direction towards reactants. That means reactants can't go to products, right? They're much less tendency. So less C3H6 will react, right?
Yeah, it's the difference between having more and more reactant. If you have more, less will react.
Yeah.
Well, you have, think of it this way. K is products over reactants, right? K is products over reactants. So we made the products way too big. So this thing has to respond by making reactants larger, products smaller. So you have to generate C3H6. So C3H6 is not reacting. C3H6 is forming to get back to equilibrium because we have way too much nitrogen in the system, way too much product.
So shouldn't more of this C3H6 react so you can...
If you say more C3H6 reacts, I have to erase that arrow and I have to point it that direction. Because you said more C3H6 reacts. But that's totally opposite of what's going on with Le Chatelier. Le Chatelier says no. It's shifted, not in that direction, it's shifted towards reactants.
It's kind of help for me to think of it as like, it's like you're looking at Le Chatelier's principle twice. Because first you're looking at the amount of N2, and that means that you have more C3H6. Once you know that you have more C3H6, you know that equilibrium has to shift towards products.
No, no. You have too much. Stop and once. Le Chatelier does not bounce around. He's a one-direction dude, right? You add too much nitrogen, it's going to shift in what direction? And no bouncing back. It's going to shift towards reactants, okay? So that you stop. Stop the thinking. It's shifted towards reactants. Well, okay, I'm shifting towards reactants. Are the reactants going to react? No, and in essence, the product's turned into reactants because it's shifting that direction. See what I'm saying?
So then they're having trouble reacting.
It has trouble reacting, exactly. It has a lot of trouble reacting because the equilibrium is shifted
So with
towards
this
reactants.
problem, we can say, okay, what do we have the greater concentration of, and which way is the reaction going? So in this example, since it's going back to reactants, we say, well, all our reactants are having trouble reacting now.
If you want to think of it that way, yeah, then they're just building up. Because we have, it seems like they're building up, but not really because we have so dang much product. We have way too much product. It has to shift towards reactants.
But now, so if you ran the opposite of that and said, now I take nitrogen away, then I would say,
Okay, we can add that
more
one.
C3H6 reacting, right?
Exactly. Okay, so yeah, I think I just said it. What I was trying to say was like, you add like this gas.
So there's another one. Remove nitrogen gas. That's 5.
Gas thing is like the concentration.
Yeah, so but you're adding it to the C.
So you're adding it, well, you're adding it to the entire thing, but since there's more moles present on the right side, right, it's 11 to 10. So there's 11, so it's just 4.
So so are we okay with number 1? Do I need to?
Right. Yes. That's what I'm getting.
We're good.
More of that.
Number 2.
We do number 2.
We're adding
That's why I was thinking things like
2. We're adding H2O liquid to the mixture.
it's like
Oh, there should be another column here. I guess this is the hint. Na, no effect.
you see no visible effects because of Le Chatelier's principle.
Yeah, it's a dang liquid.
Pressure, then, you know that means you have more C3H6, like more.
Remember, it's the story of
So once you have more, then it's like
it's the story of the equilibrium constant. When you do not get K, you're not at equilibrium. That's the only thing that's Le Chatelier. Well, H2O liquid doesn't even show up. It doesn't show up in the equilibrium constant. So there's no argument. It's not going to do anything. No effect. As long as you don't add so much that you change the volume, right? Then that gets into another question. That's kind of like number 3. Number 3, an inert gas is added.
It's the last go around.
Okay. Is there any consensus? I hear more. I hear both answers. There's a trick to this. Do you remember what the trick was?
Looking at the number of moles.
Look at the number of moles of what state? Gases. You figure out which side has the most gas. This side has 10 gas molecules.
Oh, that's a liquid.
The other one has 5.
Yeah.
The other one has only 5 gas
So now if you're
molecules.
adding more, that's going to make more reactant, right?
Yes, in essence. Okay, now you're adding an inert gas. You're just increasing the pressure. The system pressure is pressure. You don't know what gas molecule is producing what gas pressure. So you're adding gas. The system has to reduce this pressure. So the only way to reduce it is not to shift to reactants. You're going to increase the pressure even more. That's like adding pressure, then all of a sudden, instantly, the pressure goes up even higher. That's not natural, right? You add pressure, the system has to respond to reduce that pressure as best it can. It's not going to get rid of all of it, but it can try. So it's going to shift towards the low pressure side. So if it shifts that direction, will more or less C3H6 react? More. Good. Okay. The temperature, the reaction temperature is increased. See if you can remember what the trick was for that. The reaction temperature is increased. What was the trick? Do you remember? At least how I did it. Exothermic, so where do you write the word heat? Product. So treat heat as a reactant or a product. Then you can treat it just like we do the rest of the Le Chatelier problems. Good, it's exothermic, delta H is negative. Heat's a product. You increase the temperature, now we have too much product or reactant. We have too much product, so it's going to shift this way, right? So will more or less C3H6 react? Less. Very good. You guys are getting the hang of this. Remove nitrogen gas. Will more or less C3H6 react? More. Okay. More. Okay, are you okay with that? K equals 5 times 10 to the 7th for a below reaction. What if the initial concentrations consisted of silver 1.2 to the 10 to the negative 2 molar, phosphate 1.01 to the 10 to the negative 2 molar? Is the system at equilibrium? If not, which direction would it shift? What was the game plan for doing this? If you remember the terminology, I don't know, the terminology helps me. This is a what type of problem? Not ice. It was, we called it Q. We called it Q. Reaction quotient. This is a reaction quotient problem where we calculate a Q. It's a pretend equilibrium constant. And you see if that Q is bigger or smaller than K. And then you go by that. Okay? So by using the terminology in the book, that's how I remember this stuff. Oh yeah, this is one of those Q problems because I'm not sure if I'm at equilibrium or not. So you calculate a Q. Reaction quotient. And Q is just products over reactants. What exponents should I use there, Daisy? 3 on the... Yeah, these little ones here. Yep. Yep. Well, you can use K if you want. I'm just technically that's what the book used, and because you really can't say K only if technically you're right only if you get exactly 5 times 10 to the 7th, then you can really write K. But it really doesn't matter, Albert. It really doesn't matter. Shoot. Man.
Yeah, like 57.
Did you get something like 5.7 times 10 to the 7th?
Yeah.
Good, thanks. So compare it to the actual equilibrium constant. It's not equal, so you're not at equilibrium. K is too, oh good, okay. Q is too big or small? It's too big. So we have too much or too little product. I always go in terms of product, otherwise you have to think inversely. If Q is too small, you don't have enough product. If Q is too big, I have too much product. It just helps me. Then it's, oh, I got to shift back this way then. I have too much product. Okay. Okay.
So how do you know if a number is too big?
Because 5.7 times 10 to the 7th is bigger than 5 times 10 to the 7th. I'm comparing it to this. All right? Q is greater than K.
So if the Q is smaller than the K, you have to.
Too little product. You need more product.
Oh.
So it has to shift towards products then. That's how I remember it. I don't know. Okay.
So equilibrium shifts towards the reactants. Equilibrium shifts towards the reactants.
Towards the reactants, yep. Barium chloride hydrate is dried in an oven. They give us delta H0 and delta S0. Write the equilibrium constant for this reaction. Calculate the vapor pressure of gaseous water above barium chloride. 298. Okay. Javier, how about I write the equilibrium constant?
Products over reactants.
Yeah, so it'd just be what over what? Products over reactants.
So water is gas.
Yeah, but how do we write it again?
It's still
But it's a gas though, so you can't write brackets. Gotta write the P. Okay? Is that it? Yeah. I guess you don't really, all right? But that's it. So K, that really is the trick to this question. That's how you can calculate it, because K is the vapor pressure. So the question could have said, instead of calculating the vapor pressure, it could have just said calculate K, because they're the same thing. We know how to calculate K, yes?
So the barium chloride solid.
Yeah, they have S's up there. So Javier's right. I mean, the only thing that you can write in the equilibrium constant expression is the water.
Oh, because it's the whole
Products over, they're all solids.
Oh, well, like on the CSCO,
Yeah.
on the left-hand side, how do you know what that is?
Oh, yeah, those are those hydrates. Remember we had those in lab. Some of them were .7H2O or .6H2O or whatever, and you have to find the molar mass of it. You have to add up everything. Okay. Yeah, those are those hydrates. So you remember the expression to get K? What are we looking at? Where is it? Here it is. Isn't this it? But you got to get delta G first. No big deal. Here's delta G. What does the superscript 0 mean? Now this delta G has a superscript 0. Okay, we'll put them in. What does that mean? Standard, which is 25 degrees Celsius or 298 Kelvin. Right. So we're going to have to get your delta G. And right, this needs to be 298 Kelvin to calculate your delta G. So go all the way back down where we're at. And we had, shoot, I forgot the other one already. What was it? K is E negative delta G over RT.
So is it for the T delta SD just multiply 298 times the delta S?
Yep. And watch your units, though. Did you notice this? Tricky. This one has kilojoules. The other one doesn't. So just get everything in terms of joules. An easy way to do that is just replace kilo with 10 to the third. No big deal. It doesn't look that great, but it works. Right? Then you have to worry about moving decimal places, or is it multiply by 1,000, divide by 1,000? This kilos 10 to the third, so just put it in for that. Yep. No. What homework was due today? Only if we take a quiz. You can turn it in with the quiz. If we take the quiz. Yeah, if we take a quiz today, then you can take it, come in and see me and turn it in then. Because Alyssa really wants to take a quiz. All right. So make sure you don't make any of the silly mistakes in here. So I just left the units out because I verified that they're all good, right? That they're all consistent.
Is the gaseous vapor pressure? Like, what are we solving for?
Calculate the vapor pressure. So we're trying to get the vapor pressure, but realize the vapor pressure is just K.
Oh, yeah.
That's the only reason why this works. Otherwise, we couldn't do it. Oh, we gotta know what R is. I should probably be giving you that. Do you remember what it is, though? 8.314. Good deal. Yep.
I've seen that in my report.
I should. If I don't, just ask. I'll give it to you. Where's my E button? So let's see if I did this right. I got 4.66 times 10 to the negative 4 for K. Hopefully somebody gets that.
So it's the vapor pressure in units of bars.
Bars. All right. Control. Yeah, by convention. He's got a good memory. All right. Well, K is this number. And then we have to come in and we set it over it into realize that it's the vapor pressure of water. Now you're right, and we haven't got to it, but K doesn't have units. So we have to go back and see how K was defined to actually attach units onto it. Because it's vapor pressure. Okay. Okay. How would you handle B?
Plug in 1 for K, and then solve it with your known values of delta G and R, and solve for T.
Yeah. You hear what he said? You heard Eric say he's got it. So, oh, because they call this this was way back, I'm not sure when, but we were talking about the equilibrium constant and how this is the thermodynamic equilibrium constant. So if you see a gas in any reaction, you have to write P. And not only that, you have to write P, you have to use its units as bars. That's the convention, that's convention of this K that we're using. And there's no subscript on it, so they call that the thermodynamic equilibrium constant.
We have to write that in our answer.
Yeah, you probably lose a point if you didn't use bars.
Those are the units?
Yeah, those are the units. If it was, we're used to using KC, and we were too lazy to write C all the time. But everything's in terms of concentration, but we never wrote the C. Technically, you're supposed to be writing that little C down there all the time to show that it's a different equilibrium constant. But we're kind of lazy. It's kind of like writing AQ on ions. Okay, did you hear the game plan for this for B? K is E to the negative delta G over RT. We're just going to solve for T. I think Eric said it. You know everything. Solve for T. You know what K is now? K is 1 bar.
K is 1.
Yeah, because they said the vapor pressure is 1. And since the vapor pressure is K, that will be my K. And the delta G is the same, because they said delta H and delta S don't change with temperature. You could calculate them again, but it's the exact same answer you got before. 1906, 006.
Plug in the 4.66 times 10 to the negative 4 K.
No, K is 1 bar. If you plug in the 4.66 to 10 to the negative 4, you're going to get 298 for T. They want to see what the new T is going to be. So plug in the same number for delta G, same number for R.
Take the natural log for the next one.
Natural log. Can't take natural log of 1. Ah, shoot. 0. But you can't take the natural log of 1. You get 0. One bar.
So it'd be like K chemical bonds.
I think you.
T equals 0.
Yeah, I think it is 0.
1 bar. Estimate the temperature, which would be 1 bar. I didn't even see this coming. I didn't even see that. I gotta take the natural log of both sides. You end up with. Wow. Well, that won't be a test question. I think you'd have to get something. You have to expand that exponential into its terms. This plus this, and I don't know how else you do it.
That's what you do. You go e to the negative 19,006 minus e to the
Oh.
so you just subtract that.
Yeah, that's okay. Well, let's not worry about that. Very good. NA, what did you say? NA? Oh no, this is a DWA. Don't worry about it.
You split up like the exponent into because it's like division of exponents. So
So you
can
did
split it
ln
into
of delta G
subtractions.
minus ln of RT.
I wouldn't worry about it.
I didn't even do it. I think that's just how you.
That's just part A. Don't worry about part B. I would give you something other than 1. Okay. If I gave it to you. At all.
No, he didn't finish solving it, but he came up with this.
So can you see how to set these solubility expressions up without writing ice? That would really save you a lot of time if you could. You're after solubility, which is X and ice. But if you don't have to write out the whole ice thing, life would be a lot easier. What would you get in terms of X for this? You get X squared. What would you get for this one? Oh, back up. Does everyone see how you get X squared? If you can't see for the top one, you're going to get X squared. You're going to have to write out the whole ice. Right? It's going to break up into Now, even if you do not remember the charges, your ice expression is going to work because it's going to be 2 terms. The charges have to be -2 and +2, but it would look better. But see, it's going to be X and X, X squared. So the first one is X squared. How about the next one? 2X. 2X to what power? Yes, actually 2X squared. If you can't see this, you're going to have to write it out. 2X squared and just X. So if you can't see this, then you're going to have to write out the ice. How about the last one?
2x squared, 3x cubed.
Right? It's definitely going to be 2X and 3X because you have 2 lanthanims and you have 3 carbonates. So you definitely have 2X and 3X. Then how many? 2 lanthanims has to be squared and 3 carbonates has to be cubed. Kind of see the trick what's going on here? The coefficient in the X is really the power also. You notice that? I don't like doing little tricks, but this is so.
Can you solve one of those using your ice?
All right, let's do the bottom one.
Even if it's an easy one.
Let's do the bottom one, so you can see where this is coming from. It's important that you can see it. But one thing I think is really important, that's going to be really hard to see. If you don't recognize CO3 as all one unit, as carbonate, this is really hard. My brain looks at this and I see two parts. But if you don't see two parts here, we need to review those polyatomic ions, right? So you should be able to see two parts here, a lanthanum cation and a carbonate anion. Right? You should be able to see that. If you can't, then just stop by and I'll review the. And remember, the lanthanum is going to be this charge. Carbonate has to be that charge. And I've got 3 carbonates, and I've got 2 lanthanums. Right? So it'd be 3x quantity cubed, 2x quantity squared. Okay. And you got to get x for all these and list them from least to most soluble. From at the noon hour time on Friday. And you can also stop by pretty much, well, 8 a.m. you're in lab, so probably not 8 a.m., right? You better be in lab. Like noon all the way till around 5 p.m. Tomorrow I'm free. So feel free to stop by tomorrow anytime really between noon and 5 p.m. Or whenever you get out of the lab. Whenever you get out of the lab till around 5 p.m.
pH and solubility. What's the
Okay. For 7.
Because isn't it usually like they tell you like one of the things? Oh, pH is the concentration of that OH minus POH.
Yeah, there you go. Okay. So, do you see how to do 6? No? Okay. So let's get an X for that one.
pH plus the OH plus.
Oh, we can write it here. That's 4x squared, 4x cubed. It's 4x squared, 3 times, oh my goodness. What's 4 times 27? Okay. Yep. Mm-hmm. Because this coefficient is always times the x, right? That stoichiometric coefficient is always times the x.
You just divide by negative like if I have this like POH is 5 that equals the negative log of OH minus 1 log of this OH minus. How do we get that much? So I'll just divide 5.8 by negative 1. But I think you have to take the log out of something. What's the way you can swap a log? Times? Yeah. Times. So we do like 10 to this, over 10 to this.
So that's how I would list my x's, right? From least to most soluble. Well, you don't even need to find the x. Just find the x's, then compare them. So the smallest the smallest one will be the least soluble, biggest will be the most soluble. So that's why I put a number 1 in the middle one, because his x is the biggest, 10 to the negative 4. And then I have 10 to the negative 5 would be the next biggest, and 10 to the negative 8 would be the last. Most soluble. Because x is the, remember these are concentrations in solution. So this is like 8.5 times 10 to the negative 8 molar. So that's not very, that's really dilute. 1.3 times 10 to the negative 4 molar of that stuff, oh, that's a lot more concentrated.
How did you use the 108?
Okay, first I divided both by 108. Now on that calculator that, on this one, I don't have to worry about parentheses at all with this one. So the trick, I think, is if you realize this. If I take the square root of 9, that's the same as raising 9 to the 1/2 power. Okay? Or that's the same as 9 to the 0.5 power. If I want the 5th root, right? X has to be the 5th root. That's the same as, like, of 9. That'd be 9 to the 1/5, which is the same as 9 to the 0.2. So do you see where this is coming from? So I want to raise my number, my 5, well, divide by 108, whatever I get, raise it to the 0.2 power. And that's the x to the y button. Raise it to the 0.2. So we're about out of time, but work on these.
So this we can continue working on, obviously on our own.
Yeah.
We have the review to go over with you.
So I think on Friday, if you want to come ready for this test, you give, especially these last ones are the hard ones, right? But we've done them all really already. So just you can check your notes as a model, but try not to rely on them because you don't have that crutch on an exam. So try to knock them out, and then we can work them out in class on Friday.
It won't be due until the first day after.
Yeah, but you need these are on the exam though, so you don't know which ones.
So solubility of this is fixed at
Exactly.
2.
So you put that, whatever that concentration hydroxide corresponds to, you put it right there. And don't even worry about how it got there. That's just it.
Okay, yeah, that's what I was going to ask you. So we figure out the
Yep.
pOH, and to get log off, we raise it to the 10.
Yep, exactly.
Okay, so to both sides of the 10, got that, and these two cancel out, right? So that should leave me
Oh, I
with-
think you lost a minus sign somewhere.
Okay, because it's like pH minus pOH, right? So
5.8.
14
It has to be 10 to the negative. See how you wrote negative? 10 to the negative 5.8.
Okay. So like you divide that negative over, and then you take it. Yeah. I see what you're saying.
Let me stop
If we do
this.
that, we would have to look up solubility for